afternoon, welcome back. This is lecture 35. So today, as always, let me begin by going over what we did last time. Last time we discussed, we said that supposing you have LDPC codes and let us assume that they are being decoded using belief propagation decoding. And I pointed out that belief propagation decoding is nothing but the message passing algorithm that we used when we were decoding our code 742 code, for example, using the junction tree. Okay. So, that has an interpretation in terms of beliefs. Then we said that okay, over the junction tree we passed messages which were beliefs, and these beliefs were functions and involving probability of a variable taking on the value 0 and probability of the same variable taking on the value 1. Okay. So, these were the two components of a vector that we would pass from node to node. But then it turns out that since the sum of the probabilities is 1, it suffices to pass on their ratio, and their ratio is really the likelihood ratio. And so, what we do is it turns out that it is practically simpler to just pass the log likelihood ratio, and you do not lose any information in the process. So, in terms of log likelihood ratio, if you apply the same message passing rule that you adopt with junction tree, then what you actually find is that the message rule at a check node boils down to just that the output log likelihood ratio is the sum of the input log likelihood ratios, and then at a check node it is a little bit more complicated. The log likelihood ratio that is coming at the output is that is related to the tan hyperbolic function. There is an inverse tan hyperbolic and a tan hyperbolic. And we verified that this particular message passing rules I mean message passing rules as translated into log likelihood ratios, we verified that they actually satisfy the two symmetry conditions that we had required. One was that actually you would have variable node symmetry, and then you have check node symmetry. In the variable node symmetry, we need that signs actually factor out, that is, if all of them flip sign, then the output also flips sign, which is clearly the case. And at a check node, we simply require that if you multiply each incoming message by a plus minus 1 symbol, then what you get passed at the output is the product of those plus minus 1 symbols. And that happens basically because your the tan hyperbolic is a monotonic function, it preserves the sign. Okay. So, then now we are interested in performance analysis. So, what does that mean? We want to interpret each message as an indication of whether the corresponding variable is a 1 or a 0, okay, in terms of plus minus 1, whether it is a 1 or a minus 1. Now, when the plus minus 1 domain 1 corresponds to 0 in the 0 1 domain, as you know. So, and we assume that the all 1 code word was actually transmitted in the plus minus 1 domain, and in that situation any so that means you would expect that if your message was correct, that the probability that xt is equal to 1 given the evidence is greater than that, or at least you would like that to be the case. So, you interpret, and since that is greater than 1, the log would be greater than or equal to 0. So, you interpret a non-negative message as a correct message and a negative message as an incorrect message. And in performance analysis, you are actually interested in trying to find out, well, what is the probability that my message is actually incorrect. But rather than do that, what we actually do is we carry out something called density evolution, where we actually try to determine not just the probability that this takes on a negative or a positive value, but actually the entire density function. We look at the density function at the density functions that are incoming, and we provide using the incoming density functions, we actually provide the outgoing density function both at a variable node as well as a check node. So, that took us that involved quite a bit of computation. Part of the complication comes because although it is fairly easy to figure out how the input output relationship is derived in the case of a variable node, because after all you are just taking the sum of the log likelihood ratios, and by our independence assumption, which comes from the tree like neighborhood tree like neighborhood of each node assumption to depth 2L, where L is the number of iterations, then it's easy to see that the density function is the convolution of these, and you can use the Fourier transform to convert that to an multifold product. Okay. So, that is how we take care of the density, relating the density at the output to that at the input. At a check node, things are a little bit more complicated. So, here what happens is that you have the incoming density functions and the outgoing, and they are related by this tan hyperbolic function. Now, you might think, and I have said this in the last lecture as well, that given that there is a product relationship, although in terms of the tan hyperbolic function, that you might actually take the logs and try to reduce it to a sum, as in the case of a variable node. The complication is that the tan hyperbolic can take on both positive as well as negative values. So, there you have to exert slightly more effort. So, what you do is you break up the tan hyperbolic into a sign part and then a magnitude part, and that complicates things. So, that is what we actually did. We break this up into a sign part and a magnitude part. Okay. So, that is the sign here and then the magnitude, and so here is your tan hyperbolic, and the sign part is over here. The sign function, we want it to be a 0 1 function for convenience and tractability. So, if you like, you can think of -1 to the sign as the true sign of this function. Okay. So, this is the sign function that we will use, and then in place of the magnitude we will actually take the logs and a negative sign. So, this negative sign here and the use of a 0 1 sign function are just have to do with convenience and tractability, but conceptually you are just taking the magnitude and the sign of the tan hyperbolic prior because you want to separate the sign and the magnitude. And then as a result, so when you do density evolution, you have an extra step both at the input and the output. At the input, the density function on the L1s is converted onto a density function on the pair x and y, and then here at the check node you have the product of all of these, and then at the output what happens is that you have an inverse transformation that actually takes place. Okay. So, you have to take the incoming density, transform it, then you actually go through a multiplication, and here what you do is you make use of characteristic functions to actually relate the output density of this pair to the input densities of these pairs. Okay. And then you do the inverse transformation. So, if you do all that, so what you really are doing from an abstract point of view, you are saying, well, whenever I pass messages, I am using a mapping from one alphabet to another, but then corresponding to that mapping there is a corresponding mapping involving density functions. Okay. That is the abstract viewpoint, I will not dwell on it. And so, we went through the computations. This is where I discussed the tree like independence assumption. Here is where we did the characteristic function calculation, and here is where we interpreted the characteristic function in terms of Fourier transforms. Here we did the somewhat messy calculations involving transformations across the transformation T and its inverse. Okay. So, at the end of all of this, what we were able to do, we were able to actually go through a round of iteration, that we were able to translate incoming density functions to outgoing, and then the outgoing here are the incoming on at a check node. So, at a check node we go through. So, we start by transforming densities at A, then across B, which is across these transformations, then at C, and finally at D. And that point we've carried out all the transformations that we need to actually, so we finished one cycle of iterations, right. We have gone from an incoming density function back to an incoming density function. Okay. So, that was density evolution, and so in practice what you would do is you would actually carry out this computation. You would recursively compute the densities, initializing with the density function of the incoming random variable, which is L naught. You will actually use its incoming density function, and that is what will actually feed this entire process. Okay. Over the Gaussian noise channel, you can actually show that the log likelihood ratio itself has a Gaussian density function. So, what actually drives this entire process is that the incoming density functions are Gaussian with the mean equal to determined by the fact that your code symbols are assumed to be +1. Okay. So, that is density evolution, and today what I thought we will do is what is the logical next point to do is to prove something that is convergent, called the convergence and concentration theorem for LDPC codes. So, again so my reference for this is this February 2000 paper. So, I will just begin with a quick recap. So, we completed discussion of density evolution with respect to the belief propagation decoding of LDPC codes, and our reference has been for this the paper that I believe I mentioned earlier to you, namely the capacity of low density parity check codes under message passing decoding. So, the authors are T. J. Richardson and Rudiger L. Urbanke, and this is an IEEE publication. It is the IEEE Transactions on Information Theory, and this is February 2001. Okay. Now, all right, with that reference, let us get back to the title of today's lecture, which has to do with convergence and concentration theorem of LDPC codes. And let me motivate it in this manner. So, here when we were working with LDPC codes and belief propagation decoding, what we assumed was that is if so this is the tanagraph of an LDPC code. So, we are assuming that the tanagraph of your LDPC code is tree like to a depth that every node in the tanagraph has a tree like neighborhood to depth 2L. So, what do I mean by that? Well, I mean that if you actually come here, so here is our computational tree. So, what I mean is that when you unravel the tanagraph and actually come to the computational tree, then you actually notice that none of the nodes actually repeat. So, if you look across the variable nodes, there is no repetition. Okay, so, that means that there is no loop. For example, if there was a 4 here and there was also a 4 here, that would be an evidence that you would actually have a cycle. But here all the nodes are different, so that means the neighborhood is tree like. Okay. So, under this assumption, what we actually did was we found out the probability that the messages that you passed will be incorrect, in the sense that they are carrying the wrong sign that you would expect if you were actually, if your messages were indicating what should have been indicated. Okay. Now, on the other hand, it is actually very difficult to actually construct an LDPC code whose tanagraph is tree like to a neighborhood. Let us say you are doing 20 iterations, that would mean that you would require your tanagraph to be tree like to depth 40. Now, that is very difficult to construct. So, what needs to be, but on the other hand, even in practice people have found that you do not really need a neighborhood that is tree like in order to get excellent performance. If you randomly construct a tanagraph, yes, it is going to have a few short cycles, and that does not seem to affect the performance greatly. Okay. So, what this seems to be calling for is, well, an explanation saying, okay, your theory on the one hand requires that the neighborhood be tree like. On the other hand, when we observe things in practice, it seems like you really do not need it. Okay. So, that is the gap that today's lecture will try to fill. Now, I am not in a position to give you all the technical details, but at least I will tell you roughly how the proofs go. Okay. So, that is the concentration and convergence theorem. In a nutshell, what they actually tell you is that it is true that belief propagation tells you that, look, you do density evolution, and that if your neighborhood is tree like, density evolution will tell you that yes, your code is going to perform very well. Of course, you have to look at you have to actually assume certain channel parameters and carry out density evolution, which is of a computational nature. I guess in our lecture series here, what we have been doing is concentrating more on the principles of these things. So, if you do carry out this density evolution, then you can prove, then you will see after you follow through with those steps for whatever number of iterations you need, that you are going to get very good performance as long as your channel is not very bad. Okay. So, that is great, but now we want to actually say that supposing I do not have a tree like neighborhood, am I still okay, and this attempts to answer that, and the answer will actually come in two steps, because it will say that, look, if you pick a graph at random, okay, and if you average over the ensemble of graphs the performance, then the number of incorrect messages on average across a random ensemble of tanagraphs will be close to the number of incorrect messages passed, assuming a tree like neighborhood. So, on the one hand you have a collection of tanagraphs, and you have that their average performance is close to the performance that you would expect in the case when the neighborhoods are tree like. So, that is one. Then the second thing is that, on the other hand, if you pick a random graph from this ensemble, with high probability its performance is going to be very close to that of the mean. Okay. So, when you put these two together, it tells you that if you pick a random graph, and even if it is not tree like, the number of incorrect messages is with high probability for large block length n, that is important, is going to be with high probability is going to be close to the number of incorrect messages which are being passed in the tree like case. And in the tree like case, you can verify through density evolution that the number is small, that the number of errors is small, and therefore you get good performance. Okay. So, that is the connection we want to make. So, with that lengthy introduction, let me just begin writing. So, here is the theorem. For any epsilon greater than 0, you have the following: A, the probability that z minus the expected value of z is greater than n dv epsilon by 2 is less than or equal to 2 e to the minus beta epsilon squared into n. And this result we will term as concentration around the mean. Now, I will explain in a little bit what all these settings, what all the symbols mean. Right now, I just want to put down the formal theorem. Then B, for any epsilon greater than 0 and n greater than 2 gamma by epsilon, the magnitude of the expected value of z minus n dVp is less than n dV epsilon by 2. Okay. At the same time, I would like to give these equation numbers as well. So, let me box this. Okay. And let us call this equation 1. So, then this is equation 2, and this one will actually term as convergence to the cycle free case. Okay. And finally, we have C for any epsilon greater than 0 and n greater than 2 gamma by epsilon, we have the probability that z minus n dV epsilon n dVp n dVp is greater than n dV epsilon is less than or equal to 2 times e to the minus beta epsilon squared n. So, this is 3. And we will label this as concentration around the cycle free case. Okay, so that is a lot of symbols and a lot of writing. Let us see what these symbols mean. So, where? So, now I am going to describe the setting of the theorem. 1, the probabilities are computed over all choices of dV, dC regular codes and over all channel realizations. Two, Z is equal to the number of incorrect messages passed from the NDV variable nodes to the R DV check nodes in the Lth iteration. So, what that means here is that, so let me try to draw a picture here. So, here you have your variable nodes, and let us say that this is a variable node, and here you have a check node, and what you are doing is, of course, you have the input from the channel, but you also have input coming from the incoming edges, you have your outgoing message. And let us say that this is taking place along the Lth during the Lth iteration. Now, remember, the way our iterations go is that the whole iterative cycle is begun by starts with the information that you receive across the channel, and then during the and then you pass that, the variable nodes pass this information across. So, perhaps I should show a quick picture of the Tanner graph. So, just a quick reminder, the way your iteration starts is that whatever comes into the channel is passed on to the check nodes. Okay. You might consider that the message passed during the 0th iteration. Thereafter, your first iteration starts. The iteration begins when the check nodes actually transmit messages to the variable nodes, followed by the variable nodes sending back messages to the check nodes. One back and forth message passing constitutes an iteration. So, what we are talking about is the Lth iteration. So, that means that once this has taken place L times, and you are looking at the second phase of the iteration, during which the variable nodes are talking to the check nodes. Okay. So, that is the instance, that is the moment that is actually of interest. So, we are passing messages from the variable to the check nodes during the Lth iteration. The other point I want to make is that now there are typically in the Tanner graph, we have always maintained n as the number of variable nodes, but I think I have sometimes used m, little m, as the number of check nodes. But for the purposes of this lecture, however, I am actually going to use r. Okay, so, that is where this r came up, right. So, perhaps it is worth putting in brackets that we will r denotes the number of check nodes. And in addition, we have that NDV is equal to RDC, all right. Okay. Now, so all of this is trying to explain what the terminology in this theorem is all about. So, the Z here, the Z is the number of incorrect messages passed during the from the variable nodes to the check nodes during the Lth iteration. So, that is that during the Lth iteration, if you think about all the edges that are going from a variable to a check node, and you count how many of them incorrect just based on the sign. If the sign is negative, then that is considered, if the sign of the message, because these messages are real numbers, if the sign of the message is negative, you consider that an incorrect message. So, in the Tanner graph, you are going to have n dv edges, n dv is the same as r dc. So, you are going to have this many edges and this many messages, and the messages are going from left to right, okay, from a variable to a check node. And Z is a count of the number of messages that are incorrect during the Lth iteration. Now, in the theorem, L does not appear. The reason being that we assume that there is a fixed number L, say 20, that you are interested in, and the whole theorem is about that number L. Okay, so, that number L is kind of in the background, and you say yes, that is the number of iterations that we are talking about. Okay, but the theorem and its notation focuses on other things. So what are the other things? Well, it tells you that, look, I am interested in knowing there is an average, that is, okay, now when you take an expectation, you are averaging over what? Well, we are doing performance analysis assuming the all one code word was transmitted. So we are not averaging over the choice of the code word. So what are we averaging over? So we are averaging over the channel realization, and also we are averaging over the random ensemble of dv/dc regular graphs. Okay, so how do we get these dv/dc regular graph ensemble? Well, you see that you actually have this Tanner graph and there are n dv edges. Okay, so what we do is we select these edges in such a way that you get a uniform degree on the left and on the right. Okay, very shortly I am actually going to show you a picture that explains that part about the ensemble of dv/dc regular graphs a little bit better. For the moment, let me continue. So what we have is, this is saying that the deviation of z from its expected value, the probability that it deviates appreciably is small. Okay, that is how you should read it, and epsilon is a small number that you can choose, n is the number of nodes, dv is the degree of the variable node, and now beta, the parameter beta is a constant that is independent of n. It is only a function of the degrees of the check in variable nodes, and again you have n. So this is dying exponentially with n, so that means it is dying very fast. So the probability that it deviates significantly from its average is small. Okay, so that is why it is called the concentration around the mean. This theorem says that, look, now this ensemble does not assume a tree like neighborhood. Okay, so when we do this expected value, on the other hand, this is saying, look, this expected value, average computed over all dv/dc regular graphs without regard to whether neighborhood is tree like or not, is close to n dvp. So what is this p? It turns out that this single parameter p summarizes all the information that we have been able to pick up from density evolution, because density evolution tells you that I can tell you the probability, okay, with which a message passed during the nth iteration will be incorrect, assuming a tree like neighborhood. Okay, and since, because just by checking the probability that the sign is negative. Now the total number of incorrect messages, or the expected value, given that any particular edge is incorrect with probability p, is then n times dv times p. So you should interpret this as the expected number of incorrect messages passed in the tree like case. So perhaps we should write that out. So let me spell that out. You know what, I think that I will actually take the trouble to write this on a separate piece of paper, because I consider this to be important. So let's duplicate this page. So I just want to mention here that P below is the probability of an incorrect message being passed during the lth iteration in the tree-like case. Okay. I notice on your screen that it does not show up very well, this particular choice of color. So, let us change that to blue. Okay. So, I think that is better. So, this is then P is the probability of an incorrect message being passed. So, in fact, all of density evolution or all the information that we pick up from density evolution is thus collapsed into the single parameter P. So, let us just make a note that it is derived using density evolution. All right. Okay, I just wanted to make sure that I have my pages in order. Let us just quickly zoom in onto our lecture. So, everything seems in order. We have our theorem here, and then I am explaining over the course of the next few slides, I am explaining the notation of the theorem. So, that seems okay. Okay. So, now I have explained, so I explained at length what this parameter P is. So, what this is telling us that the average, so this is then the expected number of incorrect messages in the tree-like case, and this is saying that the difference between the expected value in the general case, that is not necessarily tree-like, averaging over all tanagraphs, DV-DC regular tanagraphs, and the average over the tree-like case is not very different. That is, provided you make n large enough, you can actually make this difference small. Now, you can actually put these two together and actually come up with this result, which says that therefore, the probability that if you pick a DV-DC regular tanagraph at random and then you do decoding on it, you carry it out decoding up to L iterations, that the difference between the number of incorrect messages that you will get from this random graph and the average that you will get in the tree-like case is with high probability small, or rather the probability that it deviates significantly is very small. Okay. So, that is called concentration around the cycle free case. So, the third property really follows from the first two. So, we only have to prove parts 1 and 2. Now, it turns out that the proof of 2 is quite straightforward. Proof of 1 is not. So, it involves some martingale theory, and it is not difficult, it is just that it is rather lengthy. I just finished teaching that to the regular class members here, and it turned out to be rather lengthy. So, I decided that I am actually just going to not pursue that, so that we will have a little bit more time to discuss some of the other algebraic codes that we would like to cover in this course. Okay. All right. So, continuing our explanations for what the various symbols in the theorem mean, finally, we have that also in the theorem beta equals beta dV dC L and gamma equals gamma dV dC L are constants. Okay. So, with that I think I have explained all the notation in the theorem. You know what you know that beta is a constant, epsilon is a number, small number that you can choose. Think of it as a very small quantity, n is the length of the code, z is the number of incorrect messages, and dV is the degree of the variable node, and again here you have some of the same variables appearing. The only other thing that I would like to actually explain is that I am saying that you are averaging over the ensemble of dV dC regular codes. So, what exactly does that mean? So, the way you can get your hands on this ensemble is to actually look upon the tanagraph in this way. So, we have the variable nodes. So, let me draw a few variable nodes on the left. And then you have some check nodes on the right. Now, each variable node is associated to a certain degree which we will call, which is dV, and similarly each check node is associated with a certain degree. So, that means that we have here we have n variable nodes, each of degree equal to dV. So, this number here is dV, which in this case is 3. Now, analogously, we have R check nodes each of degree equal to dC. So, this number here, oops. So, this number here is dC. Okay. And now, what we mean is that we get this ensemble of dV dC regular graphs, okay. And let me cut this out and paste it on the next page. So, you get this ensemble just by saying that, look, I need to make sure I think of each of these variable nodes as having sockets. So, you regard each of these as having sockets. So, each variable node is associated with dV sockets. And similarly, each check node is linked to DC sockets. Now, we know that N dV is equal to R dC. So, that means that if you count the number of sockets on both sides, they are the same. So, then constructing a dV/dC regular graph is then simply a matter of actually drawing lines connecting a socket in here with a socket in there. Okay. And mathematically you can actually view that as a permutation. Okay. So, there are N dV factorial possible tanagraphs preserving the dV/dC regular property. Now, there is one issue that that might cause you to think a little bit, namely that look, if I am actually drawing these connections like this at random, isn't it possible that I will draw connections from the same variable node to the same check node, and I will have more than one. Okay. Now, that can happen, but it turns out to be not terribly important. So, in the vast majority of cases you will not actually get repetitions of that type. But even if it does not. It turns out that you can average over those graphs as well. Although in practice you will actually not use a graph which has multiple edges between the same pair of variable and check node. Okay. But in the interest of time, I am not going to pay attention to that. So, let us move on and ignore that. I will refer you to the paper if you want to actually see how that is handled. Okay. So, now this explains the last part of the theorem, because right in the beginning when I actually introduced the theorem, I said that look, the probabilities are computed over all choices of dV/dC regular codes. Okay. So, what this is doing is this is explaining what this class collection of codes over which you are averaging. Okay. It is namely the collection that is obtained by actually treating this as a permutation and determining which socket is connected to which socket on the right. Okay. So, that is the ensemble over which you will actually average. Now, now let us go ahead and prove. So, as I told you, in this theorem I am only going to prove part 2, okay, part B. It turns out that part A is a little bit technically involved. It involves martingales and is not particularly difficult, but somewhat lengthy, and by putting parts A and B you actually run into part C. We will only prove part B here. Okay. So, we will say proof of part B of the theorem. Let Zi be the number of incorrect messages passed along the ith edge ei during the lth iteration. So, that means here what we are doing is we are assuming that these edges here are numbered in some serial fashion, and let us say that this is the first edge. Maybe you count from the left first, you use the sockets to determine the number of the node edge. So, Z1 is the number of incorrect messages passed along this edge during the lth iteration. Now, you might say, what does that mean? After all, there is only one message that is passed. What do you mean by the number of messages? Well, that is true. So, the number of incorrect messages passed along an edge during the lth iteration is either 1 or 0. Okay, so, it is just a 0 1 0 function. However, let us say that it is 1, it is 1 if the message is incorrect, right, and that happens with a certain probability. Okay, so, that is what we are interested in. So, the Zi take on values 0 or 1. So, let us mention that as well. Then of course, it is true that then Z, which is the total number of incorrect messages, is the sum I is equal to 1 to n dV Zi. Therefore, the expected value of Z is the sum I is equal to 1 to n dV, the expected value of Zi. And now we are going to, what we are going to do is we are going to compute this by conditioning. Okay. So, let us focus on a particular individual term, expected value of this. So, we will focus on that, and this will tell us that the expected value of Zi is the expected value of Zi given that the neighborhood of that particular edge is tree like, and I am going to abbreviate that with TL, times the probability that the neighborhood is tree like plus the expected value of Zi given that the neighborhood to depth 12 is not tree like times the probability that the neighborhood of that edge to depth 12 is not tree like. Okay. So, we are breaking this down, we are conditioning and computing the expectation. Now, it turns out, as far as this particular quantity is concerned, it turns out that when n is large, so TL is tree like. Okay. So, when n is large, turns out that the probability that the neighborhood of a given edge is tree like to depth 12 is greater than or equal to 1 minus gamma by n, where gamma is a constant. Okay. So, what that means is in this expression here, we know, of course, this being a probability is upper bounded by 1, but we also now have a lower bound that it is greater than or equal to 1 minus gamma by n. Okay. I notice that we just have about a little under 2 minutes left. So, I think what I will do is let me just quickly summarize what we have talked about, and I will finish the proof in the next lecture. So, today I spent a fair amount of time actually going over belief propagation, decoding and the associated density evolution, because in some sense I thought that that was one of the harder parts of this course. So, I went over that, tried to go over that carefully just in a descriptive sense, and then after that we said, well, that all applies under the assumption of a tree like neighborhood. What if you do not have a tree like neighborhood? So, there we have to prove that even when the neighborhood is not tree like, with high probability you will get behavior that closely approximates that in the tree like case. Okay. So, that is what we are in the process of doing. I have stated the theorem, I have explained the setting of the theorem, and we started to prove it. We will quickly wind up in the next class. So, with that, let me stop and thank you.